Hi, welcome to this lesson on analytical geometry, circles, part 1. Let's have a look at the equations of circles with center origin. Just as we can describe circles in the plane using geometrical tools, such as we've seen in circle geometry, we can translate those ideas into an algebraic setting. So we will derive the formula or equation for a circle on the Cartesian plane where the center can be at the origin, 0, 0. In this case, this is what we'll look at first. Or in the next section, we'll see that we can have equations of circles where the center can be any arbitrary point given by the coordinates c, h, k. So let us first analyze the equation of a circle in the plane as follows. So let's consider a point P, call it xy, and the origin point 0, 0 in the Cartesian plane. And let us construct the straight line between O and P. And then we'll let the distance of OP be denoted by the value r. So this distance that we're going to construct is essentially going to be the radius of our circle. So we now have a right angle triangle POX, and we can use the Pythagorean theorem to deduce the equation of a circle with the center origin as follows. So as previously mentioned, we have the origin, which will serve as the center of our circle, and we have this point P that'll be a point on the circumference of the circle called xy, such that if you drop a perpendicular to this coordinate capital X, which has an x value of x and a y value of 0 because it's on the x-axis, we can see this creates a right angle triangle. And essentially we're going to look at the set of all the points. So another point Q, another point R, another point S, and so on. We're going to keep looking at all these points such that the distance from the origin to that point is the same fixed length r. This is going to generate a bunch of points, and the points, that collection of those points, are essentially going to be the points of the circle. Okay. So again, we notice here that, again, we call this radius length OPR, and we can denote, since we've called the coordinate pxy, then the distance from the origin to this point, capital X here, is x units, and the distance from x to p is just the vertical distance y units. So that is what we have here. So from that, we can use the Pythagorean theorem, right? So the center is the point 0, 0, and any point pxy that is r units away from that center O will satisfy the following equation. So as we saw earlier, that point x here, x0, that had a distance of x. This had a vertical distance of y. So by the Pythagorean theorem, x squared plus y squared is the hypotenuse squared, which is r. So this equation here is the equation of a circle with center origin. So notice that this looks a bit different from functions we usually see. With functions we usually see, there's usually one variable. In this case with a circle, there are two variables to consider, x and y, and they work in tandem with each other and are related to the radius of the circle by this equation. So a circle, by definition, is a set of points in the plane that are all equidistant from a center point. So the center point being the origin, all these points here that we have are all the same distance away from the origin, r units. Okay, so let's consider the following example. Here we have a circle with center O and a radius of 5 units. Okay, then the equation of the circle in the plane is given by this. So all we need is the radius length, which is 5. So the equation will be x squared plus y squared. This is always the equation of a circle with center origin, and it's equal to your radius squared, in this case 5 squared, which is 25. So the equation of this circle is given by x squared plus y squared equals 25. So that is the equation of this circle. And we can see some points on the circle, right? 3, 4 is a point on the circle because if we substitute x for 3 and y for 4, then we get 3 squared plus 4 squared is 9 plus 16, which is 25. So that satisfies the equation. So it's a point on the circle. The same thing can be said for the point Q here. So if I put negative root 10 for x and square it, plus negative root 15 for y and square it, I get, well, negative root 10 squared means negative root 10 times negative root 10. So two negatives become a positive, and square root 10 times square root 10 just becomes 10. By that same logic here, this becomes 15. And 10 plus 15 is 25. So this point Q is also a point on the circle. So there are infinitely many points on this circle that can satisfy this equation for this circle. All right, so that is the equation of circles with the center being the origin point. We're going to have a look at some examples now and put this into practice. Awesome. I'll see you in the next one.